Regional metamorphism definition. Regional metamorphism is a geological process characterized by the profound alteration of rocks over extensive areas due to high temperature, pressure, and often chemically active fluids, occurring deep within the Earth's crust. This type of metamorphism typically happens in regions where tectonic forces converge, leading to the subduction of crustal plates, collision of continents, or the uplifting of mountain ranges. During regional metamorphism, rocks undergo significant physical and chemical changes without melting entirely. The intense pressure exerted on the rocks causes recrystallization of minerals, resulting in the development of new mineral assemblages and textures. The temperature conditions, often ranging from several hundred to over 1,000 degrees Celsius, facilitate the chemical reactions necessary for the formation of new minerals while maintaining the solid state of the rock. The metamorphic changes observed in rocks subjected to regional metamorphism are influenced by various factors including the composition of the original rock, the duration and intensity of heat and pressure, the presence of chemically active fluids, and the depth within the Earth's crust at which the metamorphic processes occur. As a result, regional metamorphism can produce a wide range of metamorphic rocks, such as slate, schist, gneiss, and migmatite, each exhibiting distinct mineralogical compositions and textures. The effects of regional metamorphism are often visible in large-scale geological features, such as mountain ranges, where the intense tectonic forces associated with plate tectonics drive the processes of rock alteration over vast areas. These metamorphic rocks, once buried deep within the Earth, may be exposed at the surface through processes like erosion and uplift, providing valuable insights into the geological history and processes that have shaped the Earth's crust over millions of years. In summary, regional metamorphism is a fundamental geological process that results in the alteration of rocks on a regional scale, driven by the interplay of heat, pressure, and chemical activity deep within the Earth's crust. Through this process, a diverse array of metamorphic rocks with unique mineralogical compositions and textures is formed, contributing to the dynamic evolution of the Earth's crust and the creation of its diverse geological landscapes. Regional metamorphism formation. Regional metamorphism is a complex geological process that occurs over large areas within the Earth's crust, typically in regions where tectonic forces are intense and where significant geologic events such as mountain building, subduction, or continental collision are taking place. The formation of regional metamorphism involves several key stages and factors. Tectonic forces. Regional metamorphism is often associated with tectonic plate boundaries where immense forces are at work. These forces can lead to the collision of continental plates, the subduction of one plate beneath another, or the uplifting of mountain ranges. These tectonic events generate enormous pressure and heat within the Earth's crust, setting the stage for metamorphic processes. Heat generation. One of the primary drivers of regional metamorphism is the heat generated by the Earth's internal processes. Heat flows from the Earth's mantle towards the crust through various mechanisms such as conduction and convection. In regions experiencing tectonic activity, this heat flow is intensified, raising the temperature of the rocks within the crust. Increased pressure. Tectonic forces also exert immense pressure on the rocks as they are subjected to compression, shearing, and other deformational processes. This pressure acts to compact the rocks, causing changes in mineral structure and texture. Chemical activity. Regional metamorphism often involves the presence of chemically active fluids, typically derived from sources such as groundwater or magmatic intrusions. These fluids can facilitate mineral reactions by transporting ions and promoting the growth of new minerals. They can also contribute to the exchange of elements between different rock layers, leading to metasomatism. Recrystallization and mineral growth. Under the combined effects of elevated temperature, pressure, and chemical activity, the minerals within the rocks undergo recrystallization. This process involves the dissolution and reformation of mineral grains, resulting in the development of new mineral assemblages and textures. Minerals that are stable under high-pressure conditions, such as garnet, staurolite, and kyanite, often form during regional metamorphism. Textural changes. the intense pressure and heat associated with regional metamorphism can lead to the development of distinct textures within the rocks. For example, foliation, the alignment of mineral grains in preferred orientations, is a common feature of many metamorphic rocks such as schist and gneiss. Other textures, such as porphyroblasts, large, distinct mineral grains, and neoblasty, the growth of new minerals in response to metamorphic conditions, may also be observed. Metamorphic grade, regional metamorphism encompasses a spectrum of metamorphic grades, ranging from low-grade to high-grade, depending on the temperature and pressure conditions experienced by the rocks. This gradation is often reflected in the mineral assemblages and textures present within the metamorphic rocks, with higher-grade rocks typically exhibiting more pronounced mineral changes and textural features. Overall, the formation of regional metamorphism is a dynamic and multifaceted process driven by the interplay of heat, pressure, and chemical activity within the Earth's crust. It plays a crucial role in shaping the geology of regions undergoing tectonic activity, leading to the formation of diverse metamorphic rock types and contributing to the evolution of the Earth's crust over geological timescales. Regional metamorphism process. Regional metamorphism is a complex geological process that unfolds over extended periods of time and involves a series of interconnected stages and mechanisms. Below is a detailed exploration of the regional metamorphism process. Tectonic setting. Regional metamorphism occurs in regions of intense tectonic activity, such as convergent plate boundaries where continental collision, subduction, or mountain-building processes are underway. These tectonic settings create the conditions necessary for the accumulation of immense heat and pressure within the Earth's crust. Heat generation. The primary driver of regional metamorphism is heat, which is generated by various geological processes deep within the Earth. Heat flows from the mantle towards the crust through processes like mantle convection and radioactive decay of elements. In tectonically active regions, the rate of heat flow can increase significantly due to the intense deformation and compression of rocks. Temperature increase. As rocks are subjected to increasing depths within the Earth's crust, they experience a rise in temperature. This increase in temperature can reach several hundred to over 1,000 degrees Celsius, depending on the depth and intensity of tectonic activity. The elevated temperatures cause minerals within the rocks to undergo chemical reactions and transformations, leading to the formation of new mineral assemblages. Pressure exertion. Tectonic forces exert immense pressure on the rocks as they undergo deformation and compression. The pressure increases with depth, resulting in the lithostatic pressure that compresses and densifies the rocks. This pressure is essential for maintaining the solid state of the rocks during metamorphism, preventing them from melting entirely. Recrystallization. Under the influence of elevated temperature and pressure, the minerals within the rocks undergo recrystallization. This process involves the dissolution and reformation of mineral grains, leading to the development of new crystal structures and textures. As minerals rearrange and reorganize, they may form elongated or flattened grains, resulting in the development of foliation or lineation within the rocks. Mineral reactions. Regional metamorphism involves complex mineral reactions driven by the thermodynamic equilibrium conditions prevailing at depth. Minerals may dissolve, precipitate, or undergo solid-state reactions to form new mineral phases. These reactions are facilitated by the presence of chemically active fluids, which act as catalysts for mineral transformation and can enhance the mobility of ions within the rock. Metamorphic grade. The degree of metamorphism, known as metamorphic grade, is determined by the temperature and pressure conditions experienced by the rocks. Metamorphic grade is often classified into zones such as low grade, medium grade, and high grade, based on the mineral assemblages and textures present within the rocks. High-grade metamorphism typically occurs at greater depths and temperatures compared to low-grade metamorphism. Textural changes. Regional metamorphism results in the development of characteristic textures within the rocks. Foliation, characterized by the alignment of mineral grains in preferred orientations, is a common feature of many metamorphic rocks such as schist and gneiss. Other textures, such as porphyroblasts, large, distinct mineral grains, and neoblasty, the growth of new minerals in response to metamorphic conditions, may also be observed. Metamorphic facies. Regional metamorphism is further classified into different metamorphic facies based on mineral assemblages and protolith compositions. Each facies represents a specific set of temperature and pressure conditions under which metamorphism occurs. Common metamorphic facies include the greenschist, amphibolite, and granulite facies, each associated with distinct mineralogical and textural characteristics. Overprinting events. In some cases, rocks may undergo multiple episodes of metamorphism due to subsequent tectonic events or changes in the geological environment. These overprinting events can result in complex patterns of metamorphic mineral assemblages and textures, providing valuable insights into the tectonic history and evolution of the region. In summary, regional metamorphism is a dynamic geological process driven by the interplay of heat, pressure, and chemical activity within the Earth's crust. It results in the transformation of rocks over vast regions, leading to the formation of diverse metamorphic rock types and contributing to the evolution of the Earth's crust over geological timescales. Regional metamorphism results. Regional metamorphism results in a wide range of geological phenomena and rock types, each reflecting the complex interplay of heat, pressure, and chemical activity within the Earth's crust. Below is a detailed exploration of the diverse outcomes of regional metamorphism. Metamorphic rocks. The primary result of regional metamorphism is the formation of metamorphic rocks, which exhibit distinct mineralogical compositions and textures compared to their parent rocks, protoliths. These metamorphic rocks are classified based on their mineral assemblages, textures, and metamorphic grade. Common metamorphic rock types include slate, a fine-grained metamorphic rock characterized by its excellent cleavage and smooth surface. Slate forms from the metamorphism of shale or mudstone. Phyllite, a foliated metamorphic rock with a slightly glossy sheen and a wavy texture. Phyllite forms from the metamorphism of slate. Schist, a medium to coarse-grained metamorphic rock with a foliated texture dominated by aligned mica minerals. Schist forms from the metamorphism of shale, mudstone, or granite. Gneiss, a coarse-grained metamorphic rock with alternating light and dark mineral bands. Gneiss forms from the metamorphism of granite, shale, or sedimentary rocks. Migmatite, a banded rock containing both igneous and metamorphic components, indicating partial melting during metamorphism. Migmatite forms under high-grade metamorphic conditions. Marble, a metamorphic rock composed primarily of calcite or dolomite crystals, formed from the metamorphism of limestone or dolostone. Quartzite, a hard, granular metamorphic rock composed primarily of quartz grains, formed from the metamorphism of sandstone. Foliation and lineation. Regional metamorphism often results in the development of foliation and lineation within metamorphic rocks. Foliation refers to the alignment of mineral grains in preferred orientations, giving the rock a layered or banded appearance. Lineation refers to the linear alignment of mineral grains or elongated features within the rock. These structural features provide valuable insights into the deformational history and tectonic forces acting on the rocks during metamorphism. Mineral assemblages. Regional metamorphism leads to the formation of specific mineral assemblages characteristic of the prevailing temperature and pressure conditions. Common metamorphic minerals include mica minerals, e.g., biotite, muscovite, commonly found in schist and impart a characteristic shiny appearance. Garnet, typically found in high-grade metamorphic rocks and characterized by its deep red color. Staurolite, often forms elongated, cross-shaped crystals in medium to high-grade metamorphic rocks. Kyanite, characterized by its blue color and typically found in high-pressure, low-temperature metamorphic rocks. Feldspar minerals, e.g., plagioclase, orthoclase, commonly found in gneiss and other medium to high-grade metamorphic rocks. Quartz, abundant in many metamorphic rocks, including quartzite. Metamorphic zones and facies. regional metamorphism is often characterized by the presence of distinct metamorphic zones and facies, each representing a specific range of temperature and pressure conditions. These zones and facies provide important insights into the thermal and tectonic history of the region and the depth at which metamorphism occurred. Geological structures. Metamorphic rocks resulting from regional metamorphism often exhibit characteristic geological structures, such as folds, faults, and shear zones, formed as a result of tectonic forces and deformational processes. These structures provide valuable information about the strain and stress patterns within the Earth's crust during metamorphism. Economic resources. Metamorphic rocks produced by regional metamorphism can host valuable economic resources such as minerals, ores, and gemstones. For example, schist-hosted deposits may contain economically significant minerals like graphite and garnet, while marble deposits are often associated with high-quality building materials and ornamental stones. Geological landscapes. Regional metamorphism plays a significant role in shaping the Earth's surface and creating diverse geological landscapes. Metamorphic rocks exposed at the surface through processes like erosion and uplift contribute to the formation of mountain ranges, valleys, and other topographic features, influencing the distribution of ecosystems and human activities. In summary, regional metamorphism results in the formation of a diverse array of metamorphic rocks, structural features, mineral assemblages, and geological landscapes. These outcomes provide valuable insights into the tectonic history, thermal evolution, and geological processes operating within the Earth's crust over geological timescales.